Hello everyone and welcome to this presentation. My name is David Moreno. I'm an architect and currently a PhD student from Rovira i Virgili University. I'm going to show you the research from reality to point clouds, survey and analysis of St. Miquel's Church of Batea. The current architectural heritage documentation procedures are diverse, and the use of massive data capture techniques such as terrestrial laser scanning and digital photogrammetry have become widespread during the last 2 decades. This raised the possibility of developing new assessment methodologies based on 3D documentation. Numerous investigations have tested the techniques' reliability and proved their effectiveness to obtain high-precision topographical documentation in architectural heritage. This research exposes the results of using simple, non-invasive procedures for the assessment of a shape of a masonry building from a point cloud registered with a terrestrial laser scanner. The case study selected is St. Miquel of Batea's church, which is located in Tarragona. It is one of the most relevant Baroque constructions in Catalonia, due to their architectural features and decorative elements. The building mainly consists of a basilica ground plan, a transept with a central dome over a cymbordium, and a presbytery. The main body has square columns and 3 naves, which is located at almost the same height, defining an interior space of a hall church. In addition, the measurements of 48.20 meters by 26.11 meters on the ground plan and the height of 19.95 meters is remarkable. The methodology used combines 2D and 3D processes for the assessment of the geometry and takes as reference previous works. 2D analysis is mainly based on cross-sections, which allows to quantify main measures of all structural elements in detail. And the 3D analysis is based on the comparison with reference shapes, which allows a quantitative and qualitative comparative analysis of spatial elements such as the vaults and the dome. The study was based on topographic data obtained from the building in a single day with a Leica Scan Station C10 laser device. Despite the survey involving all the building, the assessment was focused on the naves and the central dome with a position accuracy of 6 mm at 50 meters. The coordinates of each point were complemented with RGB information through the photographs taken with the internal camera of the device with a resolution of 4 megapixels. The software Cyclone was used to register the point clouds in the same local coordinate system with a standard deviation of 3 mm. The maximum error of the registration process was 9 mm, which was adequate for the assessment, and the density of the obtained point cloud was more than 169 million points. After that, a 3D reshaper was used to generate a 3D mesh of the model from the selected points. The mesh density was adjusted an average triangle size of 2.5 centimeters, which was later refined using the same program to avoid aberrations due to the point cloud noise. Once the complete point cloud was obtained, the proposed methodology for the assessment of the building combined 2D and 3D processes. This allowed the adaptation of the process according to the construction elements and optimizing the study. The analysis focused on the inside of the construction. Prior to the assessment, all the fundamental construction elements were discretized, these being the pillars and pilasters, which have a codification of P, arches, A, vaults, V, and finally the central dome. Following the main parameters to be registered and established, and the corresponding 2D or 3D process to obtain them. The 2D study was based on the thorough sectioning of the construction elements and compared the difference between equal points between the elements to identify possible movements. This image summarizes the nomenclature used for every element and section. Cross-sections were made for each element, according to the main axes that define the main points of the geometry of the elements assessed. The 3D assessment was performed with the program 3D Reshaper. This software allowed us to obtain the range of distance between a point cloud and a shape of reference. The study in that case focused on the vaults and the dome, which can be fully understood in 3D. 2 variants of the assessment were performed. First, the shape of the vaults were analyzed and compared to a horizontal reference plane. A different height from the reference plane was established for the side aisles and the central vault. This approach allowed identification of difference between the vaults simply and quickly. In addition, contour lines spaced every 10 centimeters were defined from the vault's mesh to define a topography of the elements. Secondly, the central nave and the dome were assessed according to a primitive shape of comparison, a cylinder and a sphere correspondingly, allowing us to identify differences between equal elements, which at first glance might not be appreciated. The formal anomalies can be related to deviations during construction or movements of the structure after construction. The exhaustive sectioning allows a fast and easy approximation of the formal alterations that the structural elements might have suffered. In this case, pillars and pilasters, arches, and vaults. For the study of the pillars and pilasters, the possible out-of-plan points have been analyzed based on the displacements of the x-axis, measured in the upper end of the capital molding and the lower end of the base of each column. Each pillar was measured on the both sides of each axis, obtaining the measurements through longitudinal sections and cross-sections. In the case of pilasters, it was not possible to register all of the coordinates, given the existence of moldings that distorted an accurate reading of some points. This figure summarizes the measures obtained according to the elements located in the central nave and on lateral walls. It can be observed that in general terms, the range of displacements in the pillars are very low, and in the pilasters the data tend to be smaller. These values are very low and can be considered dispensable on architectural scale. As for the rounded arches between the vaults, the springing line was measured to be over 1.35 meters from the impost of each column. The arches located in the longitudinal direction have a radius of about 2.80 meters and the cross ones 2.10 meters. The measurement of the springing line presents difficulties due to the moldings, so that only the height of the quay was registered. The arches of the collateral chapels were not studied, as they present mainly irregularities that prevented a correct reading due to the moldings. This image summarizes the values obtained. On the other hand, no relevant deformations have been observed. Finally, the 2D study of the vaults made from the registration of the points located on axial axes determined their geometry. The y-coordinate of selected points are registered based on a common horizontal reference plane, located at an average height of the pavement of all the sections. This figure shows the values obtained in the vaults located on the left and right of central nave and the vaults of the latter. Here you can see the extreme values in the collateral vaults and in the central vault. The maximum difference between comparable points is 0.268 meters between points of vault L4 and R4 of collateral vaults, and 0.165 meters between the vaults C1 and C4 of central vaults. The topographical representation of the vaults revealed that most of the elements are very similar and no relevant differences can be seen. The visualization includes the maps of the vault's relative heights and contour lines spaced every 10 centimeters. This data allowed an intuitive interpretation of the vault's shape. In the case of the Church of Batea, vault L4 has the most relevant differential gradient in respect of the rest of the vaults. This is also consistent with the results obtained in the 2D study. On the other hand, this figure compares the distance distributions for each vault showed at previous image. The ranges measured represents the 69.6% of the points. As regards to the assessment of primitives, the data of comparison of the elements are summarized in a table. The central nave has been analyzed in comparison with the cylinder which best suits the geometry of the barrel vault part. The results show how the central sections fit the ideal cylinder, with the vault section near the dome is the least. As for the dome, it is compared with a sphere. A differentiation is made between the fundamental parts, ribs and shell, and a sphere is defined for each one, as you can see. The study reveals a certain segment of the upper part of the dome due to the weight of the lantern. This deformation is not uniform, and the most settled area can be related with a deformation at medium height in the opposite quarter of the dome. The method used has allowed us to parameterize the formal difference between the construction elements of St. Miquel's Church. In general terms, no relevant discrepancies were identified, so the structure has hardly suffered any formal alterations. The identified deviations usually have small values, with some exceptions, as in the case of some points of the vaults. Nevertheless, taking into account the size of the building, most of them have no impact on its stage of conservation, although there are some trends that should be noted. Cutting planes has revealed that the leaning of the pillars do not have the same value in parallel faces. There may be a certain execution error, but it is striking that systematically the highest values in the longitudinal sections are produced towards the main facade, while in the cross sections they tend to be higher on the faces closest to the perimeter walls. No differential movements have been observed between the parallel faces. The average value of the displacement in X is 0.034 meters, with those of greater magnitude is in the pillar 2.2 and 3.2, which are caused by the action of the dome. It is also worth noting that the displacement of the pillars in the longitudinal directions tend to decrease from the dome to the main facade, while in the cross direction they tend to increase, although with much smaller magnitudes. These values have no connection to the lateral pilasters, which have an average value of 0.025 meters. In relation to the arches, we could see that those located on east side are significantly lower, with an average difference of 0.11 meters than the analogs. However, the height difference between the arches is 0.03 meters, with the exception of arc L6, which is 0.19 meters lower than the others. In the case of west arches, they maintain a maximum difference of 0.08 meters. And finally, the central arches have increased height of 0.38 meters from the dome to the main facade. As for the vaults, the graphs show that on the side aisles, the cross-axis of the vaults tends to be horizontal, while the longitudinal one is pointed towards the quay. This situation is reversed in the case of the central vaults. The 3D study has also shown a great similarity between analogous elements, although some alterations have also been identified. For example, vaults L4 and C1 have a height significantly lower than their peers. In addition, it can be seen that the left vaults are noticeably lower than the right ones. Finally, we observe that the central vault is higher from the dome to the facade. Additionally, the study of the dome revealed a certain segment of the upper part, due to the weight of the lantern. This deformation is not uniform, and the most settled area can be related to the deformation at medium height in the opposite quarter of the dome. It is also remarkable that ribs did not reproduce the same difference as the shell. In any case, the value remains small, with a maximum distance of 0.045 meters. In conclusion, the use of massive data capture techniques such as terrestrial laser scanner not only provides accurate geometrical information, but also valuable data about its structural state. This study has proposed a systematization of 2D and 3D operations to analyze a case study based on a point cloud. Thus, it is possible to identify formal alterations that would otherwise be impossible to determine, and which can have an impact on the conservation of the building. In the case of the Church of Sant Miquel of Batea, the study has given quantitative and qualitative data about the formal anomalies of the construction elements. Most of those anomalies are not related to degradation processes, since there are no cracks or other related movements. The methodology used can be easily exported to other buildings, and in fact it is easy to find many examples of formal studies based on a point clouds. Otherwise, it is always necessary to adapt to each specific case, since the characteristics of the buildings, such as size, decoration, or complexity among others, can affect the data that can be analyzed. Further research showed that the analysis of the exterior of the building and the extradors of the walls. In addition, the numerical analysis of the structure should reach some light over the displacements identified. Finally, the study of the architectonic rules and possible influences, together with a historiography of the building and its context, would complete the understanding of the construction features. That's the end of the presentation, and thank you for your attention.